is Research Methods, Unit 7, Part 1, on factorial experiments. So true experiments are procedures in which scientists have control over all aspects of the design of a study. And so it's not the case that people are coming in with feature characteristics, but a experimenter is controlling what scenario is going on that the participant is experiencing that might influence their performance. In other words, the experimenter manipulates the independent variable to see its impact on a dependent variable. Now this is distinct from a survey because surveys, generally speaking, don't have different groupings that you would put people into. So everyone gets the same survey, everyone's asked the same questions. It's not the way a true experiment occurs. And it's distinct from correlational research because correlational research is that kind of study in which people come to the lab with a particular feature about themselves, whether it be their age or their gender or their opinions about politics, and they already come to the lab. It's not like a manipulation. So, for instance, one could do an experiment in which one randomly assigns people into two groups. One group that reads an essay that espouses more conservative values, and another group that reads an essay that espouses liberal values, and see if that influences the degree to which people would be likely or less likely to vote for a particular political candidate. I'm just using it as an example, but that's an example of how an experiment's different from correlational research. Now, it's worth knowing some fancy terms, and you'll hear this often in a study that's an experiment, are factors, which is basically a fancy word for your independent variable. Okay? Now, these factors can be experimental. So, if I randomly assign people into a drug or a placebo group, that's an experimental factor. And they also could be correlational. So, it could be something like gender, male or female. And that's something that I want to point out now, and I'll point it out later, is that the vast majority of studies that are out there are a combination of experimental factors and correlational factors. So you'll mostly find experiments in which the two are kind of blended, and that's kind of an important thing to talk about in a little bit. Now, when we talk about the word level, we're talking about particular values that an independent variable can take. So, for instance, gender has two levels, male or female. College might have something like 4 or more levels. First year, second year, third year, fourth year, fifth year, and beyond. But experimental condition can have as many levels as you have groups that you're randomly assigning people into. So imagine that you're doing a drug trial where you're trying the drug at 5%, 10%, 15%, 20% strength. Each of those you randomly assign people into those conditions to see if having more of the drug has better prognosis. That's an experimental condition that might have 4 or 5 levels, but again, that's defined by the experimenter. Now, I've been throwing around this term loosely before with the hope that I may have explained it in the past, but I'm a little bit embarrassed to say that it comes up in the book here. And that is condition. And a condition is a group or a treatment that you have in an experiment. So imagine that you're doing a drug trial. Those that receive the drug are called the experimental condition. Those that do the placebo are the control condition. Okay, so mice that learn the maze before being put into a different maze, that might be an experimental condition. Those that are just put into the second maze without having experienced the first maze, that would be a control condition. So that's what a condition basically is a group in your experiment. And treatment usually is a condition of experiment where it is the condition that entails a specific manipulation that you're interested in seeing the change of the dependent variable as opposed to the control condition. That may have sounded very vague. What I mean here is this, is that imagine you're doing a drug trial, okay? The receiving the drug is called the treatment because that's the one that you're really interested in seeing if it worked. Whereas the control condition where people get the placebo, that's not typically called a treatment, that's more called a control condition because what that's doing is controlling for the fact that sometimes people just feel better because they're taking a pill, not because the pill is doing anything. So, those are all terms that are useful to know. Now, within participant designs, recall that these are designs in which participants serve as their own controls because they are being tested at least twice, once with a treatment, once without, or you could say once with a treatment, once with a control. So in a drug trial, a person might be tested 1 week on, their scores on a test of attention. In 1 week, they're given coffee with caffeine, and the second week, they're given coffee without caffeine. And that would be within participant design because the participants are being tested in different groups, but they're tested twice. So you can use the performance that the person has in the first group as a comparison against what they perform in the other group. So you can compare people who have decaf, their performance on the test, with when they have actual coffee. Now, it brings up a problem, though, is it the case that the order might matter? Okay, and here's a good example of it. The first week that you have a attention test, you don't know what you're doing when you do the attention test because you're new to it, just like if I were to give you some kind of a new or novel kind of a psych evaluation, you wouldn't know what it's all about because you haven't had it yet. But people who have been doing an attention test for about a week, that second week, they're naturally going to just get better at it because they're already experienced with it. They don't need to read the instructions, they know what to do, they've already had practice. So order of conditions really can influence performance within participant designs, and that's one of their big drawbacks. So when we talk about such pollution from one condition to another, you can have order effects where one condition pollutes another. So, being really, knowing the kinds of questions that are asked in one condition, if you're going to be retested with those same questions, you already know what you've been asked, so that would pollute what you would answer a second time. And other things have to do with sequence effects, where the order of conditions influences the results obtained. And that's a little bit less clear, the difference in order and sequence effects. In reality, they're kind of the same thing. The book makes a distinction, but the idea basically with both order and sequence effects is that the order in which you receive conditions and treatments influences the results of the study, such that if everyone had one treatment before and then the control, or if everyone had the control then the treatment, those two scenarios would end up with very different results because of order and sequence effects. Now, the big problem within participant designs are, as I said, the order effect or the sequence effect. I'm going to skip ahead because I already spoke about most of this. So one way that we resolve order and sequence effects is by doing something called counterbalancing. Now, when we counterbalance, what we do is initially we create two groups in an experiment. And so we randomly flip the coin to create these groups. And group one takes, for instance, if you're interested in testing whether or not performance in class or an exam is better with notes or without notes, this is kind of a classic issue in testing people, because the students always want to have the textbook or they want to have their copybook out so that they can look at their own notes. And it's unclear whether or not that actually helps. Sometimes having too much information at your fingertips makes you sort of clam up, and so you end up not getting as much done and not performing as well. So it's really unclear whether or not having notes helps. But, if you don't know that to be true, you might want to do an experiment on it. So you divide it such that group 1 takes test 1 with notes and then takes test note 2 without notes, And then group 2 takes test 1 without notes, and test 2 takes it with notes. So if you see on the slide exactly what I'm trying to say, you basically balance the order so that if it, for half of the people get A and then B as in their ordering, then the other half gets B and then A, and that's how you counterbalance. Now, the problem with counterbalancing, however, is that this only works when you have a small number of conditions. And the number of conditions that you have in a study that you would need to counterbalance is determined by using what's called the factorial. So the factorial is when you have n factorial. You multiply n times n minus 1 times n minus 2 times n minus n plus 1. Okay, so 3 factorial would be 3 times 2 times 1. And what you'll realize with factorials is that they become very big numbers very quickly. So with 2 conditions, as you saw on the last slide, there are only 2 factorial orders. And 2 factorial is 2 times 1, so you only have 2, as you can see, AB or BA. However, when you have 3 conditions, there are 3 factorials, 3 times 2 times 1. So there's 6 different orders, and when you think about it, you have ABC, ACB, BAC, BCA, CAB, CBA. Those are your 6 orders if you have 3 conditions. And I'm not going to try that for more than 3 because I would totally mess it up. Because with 4, you have 24. A, B, C, D, A, D, B. I'm not going to even do that, but you get the point. There's 24. With 5 conditions, there are 120. With 6 conditions, there are 720. And with 7 conditions, there are 5,040 possible orders. Now, the problem here is that if you were to do the kind of counterbalancing that I described above, you would need to have an equal number of people in each of the groups that you were studying. So if you had 7 conditions, you would need to have at least 5,040 people in your study. But in reality, that would only leave you with 1 person per group. So the point that I want to make here is that it's better to keep the number of factors that you have in your experiment, conditions that you have in your experiment, as small as possible. Now, there's another solution which is called block randomization. So the way in which you do that is that you forget about the balancing the exact number of groups that have particular orderings. And what you do is you just sort of randomize it. So you one time, imagine that you have 4 conditions, A, B, C, and D. One time you'll run it B, D, A, C. The next time A, B, D, C. The next time C, B, D, A. You completely randomize the order. And then you just forget about it. You don't worry about order effects. Because by randomizing it, the idea is that all of those differences might go out in the wash. But it's not possible to do this in all situations. Another solution would be reverse counterbalancing. So imagine that you have, again, 4 conditions. Half the subjects see it in order A, B, C, D, and the other half see it in the order D, C, B, A. So what you do is you have 2 orders, one going forward, one going in the reverse, and what you end up doing is just running half the people with one way, half the people with the other. That is not a great solution, but it's one way people have attempted to account for these order effects. There are more complicated ways. One of them is called Latin square, which is mentioned in in the book. And if you've ever played the game Sudoku, where that little puzzle that's in newspapers where you have to fill in numbers such that there's a unique numeral in each column row, and it's kind of like that. It's really complicated, and there are statistical tools for analyzing that, but for the most part, You're not going to find that in undergraduate level research. So in general, to solve order and sequence effects, try to design experiments to have as few conditions possible. So instead of doing an experiment like the one that you read earlier in the semester, where someone does a check with nothing on the back, with a smiley face in the back, with the words thank you on the back, and thank you plus smiley face. You know, if you want to make it, you can do that. That's great. But if you want to ease the burden, you want to do just two conditions. So maybe the condition in which you have nothing written on the back of the check, or thank you and the smiley face. So you do use what you would think would be the weakest condition and the strongest condition. And then you'd only have two. And another reason why it's better to keep it simple is that when you get above two conditions in an experiment, it requires additional knowledge about statistics. So if you ever took statistics, you remember something called Tukey's honestly significant difference test or multiple comparison tests. These are tests that are required when you have more than two groups. So it's always best to sort of stick the two. It makes things a little easier. So as I said, you know, if you go beyond two, you're going to have a more sophisticated understanding of statistics, which is great. You should understand statistics better, but understand that you're going to have to be hitting either someone who knows statistics really well or a book that describes it really well. So now we're going to talk briefly about the other kind of designs, which are called between participant designs. And I just want to point out again that in what we studied before within participant designs, participants serve as their own control. But there's a lot of experiments where you can't do this because the order or sequence effects are going to be so severe that there's no way that you can actually run the experiment twice. So a good example of that might be the Milgram experiment, the shocking experiment where people shocked another person. You know, once someone did that experiment, it's not like you can bring them back the next week and be like, hey, here's another subject who you're going to shock. There's something about that that would seem a little bit weird. Medical experiments. People either get better or they die. So it's hard to test people on multiple levels of a drug if they stop seeking treatment because either they got better or they succumb to the illness. So that's an example. And its key thing is randomization is key to between participant designs. So being able to create groups of subjects that are different only because they were randomly selected to be in the particular group that they ended up in. That is key to between participant designs. But a major limitation is that you never know. The coin could have been just a bad coin. You picked the wrong one from your pocket. And it just so happened to put a lot of really healthy people in Group A and a lot of unhealthy people in Group B, or a lot of very anxious person in Group A and a lot of anxious people in Group B. And what's happening is that the effect that you're observing is not due to the treatment that you give that's different between Group A and Group B, but the composition of the group. Now, you hope that randomization would, get rid of that. But, people do win the jackpot lottery, right? So occasionally things that are statistically unlikely to occur happen. Of course, they never happen to any of us, but that's another story. So when we talk about between participant designs, there are those in which you have two conditions. So you have, for instance, a control and a treatment, or one in which you have multiple conditions. You have a control condition and you have, say, treatment 1, treatment 2. Treatment 1 might be one particular drug that they think works. Treatment 2 would be another drug they think might work. But that's how the difference between, just a 2 within participant condition and multiple between participant conditions, how these occur. Now, I'm not going to repeat the slides that I did before because the same things apply here as with within participant designs. It's still true the smallest number of conditions is desirable. You don't want to have 50 groups of people, each containing 50 people, because that ends up being a lot of people in your study. It's very hard to get a study done when you have to collect that much data. As I say, because when you increase the number of conditions, you increase the number of participants that are required. And that's expensive. If you've ever run an experiment before, it's really easy when you have a subject pool of undergraduates that you can subject to your experiments. But, when you're doing experiments that, are outside of the, context of working with undergraduates, imagine you're doing a study on older people and you want to pay them, that ends up being very expensive. 100 people at $20 each is, $2,000. That's good money. So you have to be very careful because it gets expensive. The more groups that you have, the more potential that any given group that you form is going to have a composition that's weird, that's going to make people perform in a way in which they otherwise wouldn't. And so here are my conclusions. Within and between participant designs, each have significant advantages. So within participant designs, subjects serve as their own control, eliminating potential sampling differences in the conditions, which is good. Between participant conditions, there are no possibility of order or sequence effects, which is good. You don't want that. But they also have disadvantages. So within participant designs, you have order and sequence effects, which are really bad. And between subject designs, you have possible differences between groups in the composition of the sample, which is bad. So a solution is often to combine the two, which is called a mixed multiple factor design. And we'll talk about that in a bit. But the point here is that these are all designs which, they have their advantages and they have their disadvantages. But the one solution I can offer you is always and as much as possible exert as much control as you can in making the experimental situation be as pure as possible, as sort of close to the ideal experiment as possible, and that'll probably get you results that are reliable and valid.